Welcome. In this video, we are discussing one variable data analysis, including creating histograms, box plots, dot plots, finding numerical summaries using the calculator, determining whether or not there are outliers, and assessing normality. All right, let's go ahead and get into it. Written here, I have a list of the heights of several of my students in inches. All right, now, in order to create a histogram, this is the first graph that we're going to take a look at. All right, so in order to create a histogram, I'm first going to create a frequency table, which is going to help me to determine kind of the blueprint for my histogram. Think about if you're building a house. You're not just going to start digging the foundation before you actually have an architect write up the blueprints. So this is like the blueprints for our graph. All right, I'm going to have ranges of heights, and then I'm going to have the frequency with which they occur. So basically the general count of how many heights fit within each of these ranges. Now the thing about histograms is that they are always a continuous distribution. All right, so you are looking at, well, I guess I shouldn't say always, but we tend to draw them as though they're continuous distributions. So the bars are generally connected to one another, and that's because the way that we write the ranges of values is to, for example, the lowest value that I have here is 61, so I'm going to go up to just below, let's say 63. So I'm going to go about every 2 inches. So this would include 61, 62, all the numbers between them, as well as all the numbers right up to 63. So 62.999 repeating forever would still be included in this range of values. However, this moment you reach 63 exactly, you are going to go to the next bar. And that number is going to be counted here in this next section. And I'm going to go up to just less than 65. And I'm going to keep following this pattern all the way through. Now, why am I going every 2 inches? I have no idea. It just seemed like an easy way to count this, because it allows me to just kind of go by odd numbers since I'm starting with an odd number. If I were starting with an even number, I'd just be going by evens. And it allows me to group more than one number together. And how do I know when to stop? Well, I look at my largest value, and that determines where I'm actually going to stop with this. All right, so my largest number is 73. It's not going to be included in this one. All right, this is up to less than 73 now. If I have 73 or higher, and I do have one number that is 73, I'm going to have to include that here. So I have to have 73 to just less than 75. Now, if I'd wanted to, I could have started at 60 and gone 60 to 62, 62 to 64, and so on. I just chose to start with my smallest number. All right, you have a lot of choice when you're dealing with histograms. Now, the frequency with which these occur, I'm going to count up all of the numbers that are between 61 and 63, not including 63. All right, so I have one number right here. I have a second number. I have a third number and a fourth number, so I have 4 of those total. Right? Because I had 2 61s and 2 62s in this data set. Now 63 to 65, I'm going to include 63 and 64, and if I had any partial inches, then I would have included those as well. So let's see, 64, so that's 1. I'm looking for 63 or 64. 64, that's 2. 63, that's 3. And I don't see any more, so I have 3 total here. Now 65 to 67, I'm looking for 65 and 66. So 1, 2, 3. It looks like 3 total. And 67 to just below 69. I have 1. So I just have one of those. 69 to 71. I'm looking for 69 or 70. All right, I have one of those. 71 or 72, because that's going to be just up to 73. So 71 or 72, I do have a 72. And then 73 to 75, I have one of those as well. All right, just based on this frequency distribution, I can kind of tell that my distribution is likely to be what we call right skewed. Most of my points are grouped up on the left-hand side of this data, so on the lower side of the data, and then I have a few data points kind of stretching away from my middle. All right, now to create my histogram, these things don't have to be completely perfect, but they do have to be, you do have to be careful enough while graphing them to avoid having a misleading graph. All right, things that make a graph misleading are uneven bin widths, so uneven bar widths, starting at a number other than 0 on the y-axis, which distorts the frequency that you're actually graphing, things of that nature. So you want to kind of avoid those pitfalls. All right, so let me see. I'm actually going to tear off a few sheets of paper from my pad here because I'm having trouble getting this to fit fully on my desk. And there we go. Now we can see this a little bit more easily. Much better. Sorry about the little bobble of the camera. All right, so I want to, on my x-axis, kind of start with a 61, and I'm just going to put a tick mark for every time I'm going to be changing my bar. So 61 here, 63, 65, 67, 69, 71, 73, 75. And you always have to label your axis so that people actually know what the numbers mean. Numbers without meaning, there's no point in analyzing them. The whole point of data analysis is to better understand what the numbers are trying to tell you. If you strip the meaning off of them by not including the units of measurement, not including what you were measuring to begin with, then you basically have a pointless graph. And what's the point of completing work that has no meaning? All right, so please make sure that you always include a title on your axes. And I'm just going to use my lines from my paper as my tick marks going upwards. And these are just my frequencies. So if it occurs one time, then it's going to go up to this height, 2 times, and so on. And over here, I'm going to write frequency. You should also always have a title at the top of your graph. And this graph is going to show the distribution of student heights. I already know that the heights are in inches from my axis down here, so I don't actually have to identify it up in my title. All right, now I'm going to go through and use my frequency table, my blueprint over here, to build my graph. My bar from 61 to 63 should be 4 units high because there were 4 students who had heights within that range. Now remember, 63 is not included in this bar. 63 is what begins the next bar, which is why these are going to be touching. And then 65 begins the next bar. And notice I'm trying to keep these bars very equally spaced. The reason that's so important that your bars are the same width apart is that your eyes actually react to the area of the bars as well as the height. So if you have a bar that's like 2 or 3 times the width that it should be, your mind, your subconscious is actually going to deceive you and make you think that that particular section of the graph counts for more than it really does. So what you're trying to play to is easy reading and avoiding accidentally deceiving the subconscious of the person who's actually trying to read your data, read your graph. Statistics always gets such a bad rap because there are unscrupulous people who will use it to lie. Remember, statistics do not lie. The people who analyze the statistics incorrectly are the ones who are lying. Numbers can't lie, but unscrupulous people can do horrible things with numbers that mislead people. All right, so having a basic understanding of statistics is really vital for staying informed and avoiding being taken advantage of. All right, so this data set up here breaks down to this graph if you superimpose a little bit of a curve over this. Running out of pencil lead. That was a crappy curve. Let me try that again. If you've ever struggled to draw a smooth curve over a graph, don't worry about it. It's one of the reasons why mathematicians love writing in pencil, because inevitably, we are going to have to erase something as we're going through our work. All right, now this curve shows us that our center, which is probably more in with these numbers over here, this graph is stretching to the right away from that center. That's why this is skewed to the right. Think distortion. So if a younger sibling has ever pulled on your shirt tail and pulled it until you have like this long stringy tail, and your shirt is completely distorted, it's all messed up, and no amount of washing makes it go back to the way that it used to be. That's basically skewed on that side. So imagine this like the shirt tail that was pulled. They'd have to be pulling it on the right-hand side of your body in order to make this tail on the right side. So this is skewed to the right. All right, now that would be the shape. That means that right away, I know that I'm going to be more interested in the median and the interquartile range of this distribution than I'm going to be interested in the mean and standard deviation. Now it also means that right away I can tell that this distribution right here, this is not normally distributed. We're going to take a closer look at why that's true, but what I can see right here is that this is not a bell-shaped single-peaked symmetric curve with 68% of the data within one standard deviation, 95% within two, and 99.7% within three. All right, it's not a bell curve like this. Right? This is the shape that you look for if a distribution has a chance of being normal. So right now, because this is a right skewed distribution, I could already declare that this is not approximately normal. All right, so keep this in mind for when we get to the very last problem that we're going to be working through. Now, if we wanted to do this histogram using the calculator, all right, there are ways to do this a little bit quicker. Let's take a look. All right, very first thing that I need to do is go to my stat button. All right, so I'm going to push stat, and then I'm going to hit enter on edit. All right, so I'm going to hit enter, and it allows me to see all of these different lists. Now, it's really, really important when you are messing around with these lists to make sure that when you are trying to clear out these numbers, you can delete within the list itself, but when you scroll up to the top here to look at the entire list as a whole, never, ever hit delete. It will delete the entire list, and you actually end up having to delete all the lists, reinsert all the lists, and that's just a pain. No one has time for that. All right, so always clear the list. I want to clear out the numbers that are written here, so I'm going to hit clear. Now look at what happened. All those numbers that were listed here suddenly disappeared. They're still showing up on the screen, but they've disappeared from down below here where they were actually listed out. When I arrow back into this, or if I hit enter, all right, you can use a downward arrow or you can hit enter. Now my list is completely empty, but the list is still there. That's an important thing. The list is actually still in existence. Please never hit delete at the top of a list. It will totally mess up your calculator. All right, not permanently, but it's annoying to fix. All right, now within this list, I'm going to type in all these numbers. They do not have to appear in order. All right, the calculator is perfectly capable of reordering these for us. So I'm just going to start typing these in, and I'm just typing the numbers and hitting enter after each time. I know you can't really see my fingers moving, but you can see the numbers entering in. All right, so one thing that you can take a look at is that right next to L1 here, it has 15 in the parentheses. That means that right now I'm on the 15th blank. Let's take a look at how many numbers we actually had in this data set. All right, if we add up actually all the frequencies, 7, 10, and 4 gives us 14, so there should be 14 numbers that I just typed in, and number 70 is the 14th number. So I actually have all the numbers typed in here. And I am going to now go to the stat plot. The stat plot is written right above the y equals button. And it's written in blue, and that's what my second button is. That's the color of my second button. So I'm going to hit second, stat plot, and I'm going to hit enter on this very first option. You want to make sure that your other stat plots are off. Just have this first one on. All right, so I'm going to hit enter on that one, and I want to make sure it's on. If it's off, then you want to arrow over so that your cursor is blinking on the on, and you want to hit enter in order to actually select that option. Now right now I have it set to be a box plot. I actually want a histogram, which is the middlemost, it's the third graph over here. All right, so I'm going to hit enter to change that selection. Notice that also changed what's down here. My X list is my list of values. So where did I type my data? I typed my data into list 1. If something else is in your calculator, take a look at these number buttons down here. Do you see L1, L2, L3, L4, L5, and L6 written above those? They're written in blue. All right, now because it's written in blue, you would use the blue button in order to select that. So if I wanted to change which list I was dealing with, I could hit second 2 and list 2 would pop in instead. Second 3, list 3 would pop in. If you have something other than list 1, second 1 will make list 1 appear. All right, it's very important that you actually use these list names down here instead of trying to type it in using the alpha keys. That's really not going to work. It doesn't mean the same thing to the calculator. Now this frequency thing right here, I typed in every single number exactly the number of times it appeared in my list. So I don't need to have a frequency. Each number is typed in with a frequency of 1. All right. So this is set up the way that I want it to be. My graph is going to come out in blue. If you want to change the color, go for it. And now I'm going to go to zoom. All right, now zoom allows me to choose all these different options for how I want it to structure my graph. The key zoom feature that you want to pay attention to during this lesson is zoom stat. All right. Zoom stat will choose the most advantageous proportions for your graph. And notice that's a little bit different than mine. Let's take a look at why that's happening. All right, so if you want to take a look at these bars and see what's really going on, you want to trace them. And tracing them shows that this bar right here, all right, you can see it blinking on top of it, has a minimum of 61 and a maximum of 30 or 63.4. So it's not actually using even bar widths, which is interesting. I want to use even bar widths. I don't really want to deal with this kind of messiness. So I'm going to go to the window. All right, now in the window, you can actually choose, like my minimum was 61, my maximum I had it go out to 75, and I had my X scale, I was going by 2s on my X axis from my bars. All right, and I'm going to have my max Y be 6. All right, that's about what I structured my graph as. All right, my min, max, and this. All right, and now I'm going to go ahead and hit graph, and it adjusted things. All right, so if you don't like what the calculator is doing, you don't agree with where it's stopping the bar, you don't have to keep it there. You can change it. And in this case, it was a lot better for me to go ahead and change it so that it was easier to work with. All right, so now if I go through and I trace this, I can see that this bar right here has a minimum of 61, a maximum of 63 because I'm going by 2s. And the n equals 4 right here means that there were 4 students who had heights within this range. And if I arrow to the right, now I can see my next bar. So this frequency table could be built straight from the calculator to help you come up with the same graph on paper. Now, if you're working through digital work right now, I highly recommend taking a picture of a graph that you do by hand, copying and pasting that picture into a Google Doc or a Word document that you're working through to be able to get a decent graph into digital format without having to try to learn all of the digital software that you might have to use to actually get a graph like this to show up. It's also a lot easier to actually label your axes properly when it's on paper. Notice there's really no option to type that in here. All right, so this is how you would get your histogram via the calculator. Now to create a box plot, we could do the same thing. We could actually create a box plot using the calculator, and I'm going to do that for right now. All right, I'm going to go back to my stat plot, and I'm going to arrow down and over to the fourth graph, which is your box plot with outliers shown. The fifth graph shows box plots but doesn't identify if there are any outliers. This one right here will actually separate off any outliers so that I know if I have outliers. It's a nice little shortcut that you can use. All right, my X list is still list 1, frequency is still 1. If I have outliers, it's going to mark it as a box symbol instead of like a plus or tiny little dots that I can barely see. And I'm going to go back to zoom, 9, and now I have my box plot. Now, you can't see any of the numbers here, so let's figure out what these numbers are. I'm going to hit the trace button. All right, and that took me to my median of 65. So I'm going to do this. So my minimum is 61, first quartile is 62, median is 65, third quartile is 67, and maximum is 73. So I am going to go ahead and draw a number line down here. And I'm just going to start at 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for 70. 1, 2, 3. All right, so 73 is going to be out here. Give me one moment. I had something that was jostling the camera and had to remove it. All right, so let's see if we can get this graph on the paper. So the first part of my graph is 61. So right here, above the 61, I want to have kind of like a little tick mark. My next is 62. So right next to it, I want to have a longer line segment. That's going to start my box. Arrow again, 65. And I want this line segment to be the same length as the previous one. All right, this is going to be my median line. The next is 67, so about 2 beyond this. And then my final one, 73, which isn't an outlier, but is darn close, is going to be way out here. Once I have those line segments drawn in, I'm going to complete my box, connect my min and my max back in towards my quartiles. And now I have my box plot, but don't forget this number line. Remember, numbers without a label have no meaning. This should read height in inches. All right, so this is one way to get your box plot. Now, these same details can actually be found from your numerical summaries, which is what we are going to next. All right, and I'm going to keep this off to the side so that I can show you how these numerical summaries could also give you your box plot. So you might want to do 3 and 4 first, and then go back to your box plot if you don't like to use the calculator to graph. Now you will need to use the calculator in order to find your numerical summaries, because standard deviation is an absolute pain to do by hand. You can, but I don't recommend it. All right, now remember, standard deviation and by the way, to get out of a graph screen like this, hit second mode. See that little quit word up there? It allows you to quit out of that program. So just like a computer program, you quit out of it, you want to quit out of this. All right, you don't clear out of a program, you actually quit the program. All right, now standard deviation represents the average difference of each of the points in the data set from the mean. So all of those different points within the data set, how far are they from the mean on average? That question is answered by the standard deviation. All right, we use S sub x for that particular value, and we use x bar or mu for the mean. Now, minimum, our smallest number, first quartile is the middle of the lower half of the data. Median is the middle of all of the data, and third quartile is the middle of the upper half of the data. Think about splitting things into 4 sections. So you cut it in half, then you cut it in half again on either side to get 4 equal sections. Quartile meaning quarter, percentile. So a quarter of all the percents would be 25%, 75% would be 3/4, median is actually 2/4, which is your second quartile. That's why we skip from first to third. We're not actually skipping, the median is the second quartile. It's just a middle value, so it actually has a special name. Measures of center get their own name. All right, and then our maximum is our highest number. So when we want to go through and find this, again, we would want to go to Stat, Edit, and enter our data if it wasn't already there. Now I've already entered the data as you saw earlier. I went to Stat, hit Enter on Edit, typed in all of my numbers. Once your data is in the calculator, here's what you do. You hit Stat, and now we want to calculate with the data that we just entered. So I'm going to use the right arrow and go over to Calculate. All right. This one var stats up at the top stands for statistics for a single variable. All right. The next one would be statistics for 2 variables. So if you entered 2 separate lists of data, then you could actually find all of these summaries at the same time. So sometimes number 2 is very useful, but right now we just want the first one. All right. We listed all of our data in list 1, and we don't need a frequency list. We did not actually identify how frequently those numbers appeared in a separate list, so you don't have to put that in there. You just leave it blank. If you have a calculator that brings up one var stats and then opens parentheses, you would just want to type in list 1 and close your parentheses, and then you would be able to hit enter, like here, to be able to calculate. Now on the calculator here, you can see that our mean is 65.5. And our standard deviation, which is this S sub x value right here. All right, 3.897. So I'm going to make that about 3.898. All right, I rounded this up to an 8 because of the 7 that came right after it. Now, if you notice this little arrow next to the first quartile, if you arrow down, you're going to have the rest of this information appear. So this is where I'm going to get the rest of this: my minimum, my first quartile, my median, my third quartile, my maximum. So my minimum was, let me put this here so you guys can actually see, was 61. My first quartile was 62. My median, 65. Third quartile, 67. Maximum 73. Now it's really useful to know how to do this using a calculator or using a computer program, because the trend currently for real life is big data sets. All right, we have to deal with a lot of really big data, and it's very difficult to do that by hand. So knowing how to use the calculator or using Excel or some other program to be able to actually calculate this without doing it by hand is so vital. All right, so these are all my different values. This is my average. This is my middlemost number. Now notice we were right skewed with our graph earlier. All right, so our graph here, we were skewed to the right. You can also see this here. The difference between the median to the maximum is much greater than the difference between the median to the minimum. All right, so it was stretched out on the right-hand side, it's skewed to the right. Notice that the mean is a little bit larger than the median. That's the effect of skewness on this number. All right, so this median value of 65 is smaller than the mean because the mean was pulled in the larger direction by the skewness that was occurring. That's why whenever we have a skewed distribution, we want to deal with median instead of mean, because the mean is actually being falsely inflated. All right. It's larger, but that doesn't necessarily mean that most of my students were taller. Notice that most of my students are actually grouped up down in this lower end. All right, 65.5 would be more towards here as opposed to 65, which is the true center right here. It got pulled a little bit towards these higher values. So those who in my class who are a little bit taller, you actually distorted my mean. All right. Because the standard deviation uses the mean to actually calculate it, because it's talking about the average difference from the mean of the points in the data set, if you're not using the mean, you're not using the standard deviation when you go to describe the distribution. All right, so kind of keep that in mind. That means that here, for my measure of spread, I would actually want to find the interquartile range, which I have to find anyway if I want to figure out if I have any outliers. All right, now this 5-number summary here is exactly what I used for my box plot. All right, my minimum was 61, my first quartile, 62, that's this part of the box. My median was 65, my third quartile was 67, and my maximum was 73. Now, to determine whether this maximum should actually just be the upper end of this whisker, or if I should replace it with an asterisk or a star or something to separate it from the data set to show that it's an extreme value, you have to figure out, is it an extreme value? And that's where this next part comes in. So does your data set have any outliers or unusual patterns? All right, unusual patterns would be unusual clusters of points. Right now I don't really have multiple peaks. It was pretty smooth. The only thing that might be true is I might have an outlier. So let's take a look. All right, now you can have outliers on the low end. So I'm going to call those low outliers. And you can have outliers on the high end. I'm going to call that high outliers. Low outliers, you are going to take your first quartile, which is the lower end of the middle 50% of the data. So it's basically this part of this graph right here. And we're going to take the width of this box, 1.5 times that width, and we're going to look at that distance below the middle 50% of the data. Anything below that is an outlier. So the formula for this, to go to the left of the first quartile, you have to subtract, because left on the number line is decreasing, and if you're decreasing by a certain amount, you are subtracting it. All right, 1.5 to get 1.5 times the width of my box. The width of my box is my interquartile range, which we abbreviate as IQR. It's how spread out the middle 50% of all the heights of these students were. And IQR is your third quartile minus your first, which in this case is 67 minus 62, which is equal to 5 inches. All right, so the middle 50% of my students' heights were had about a 5-inch range of values. All right, so it's not super spread out. All right. Now, if I put this into here and I put my first quartile in here, I have 62 minus 1.5 times 5. 1.5 times 5 is 7.5. And if I subtract that from 62, right, 62 minus 7.5 gives us 54.5. Please be very careful of order of operations. Multiplication always comes before subtraction. Don't try subtracting this then multiplying. You always multiply before you subtract. All right? Don't forget what we used to teach as PEMDAS. Multiplication and division are considered the same level of operation as are addition and subtraction because they're opposites of each other. So anything in parentheses you need to do first, then exponents, then multiply or divide anything that needs to be done, then add or subtract whatever's left. All right, so 5 times 1.5 first, which is how I got the 7.5, then subtract it. It's really important that you do it in that order. If you try to type this into the calculator in a different order, you're not going to get the right answer. Now, 54.5. I don't have any number smaller than 54.5. My smallest number was 61, so I have no outliers on the low end. So no low outliers. Now let's look at the high outliers. I'm going to do the same sort of thing, but in reverse. I'm going to look at the upper end of my box. I'm going to go 1.5 times that width above there, which means if I need to go to the right, I need to add, and the upper end of my box is third quartile. So my formula is the third quartile plus 1.5 times my interquartile range. So I'm looking at 67 plus 1.5 times 5, which is 67 plus 7.5. And 67 plus 7.5 is 74.5. Now, you need to ask yourself, do I have any heights that are greater than 74.5? If it's exactly 74.5, it's not an outlier. It has to be larger than that. My largest height was 73. All right, so although the 73, that student is rather tall, they are not an outlier. So there are no high outliers. That's why when this was graphed, there is no asterisk over here. So this actually should stay as part of this whisker. So I'm going to answer this as no, there are no outliers. All right, unusual patterns would be like multiple modes, so like multiple peaks. You don't really have that here. Right. Now, when you go to describe the distribution, you need to describe it using your socks. Shape, outliers, center, and spread. So the shape of my distribution was skewed to the right. We've been talking about that quite a bit. I don't have any outliers. The reason you check both of these first is even if you have a symmetric distribution, if you have outliers in your distribution, you should still use the median and interquartile range to avoid having any sort of distortion occurring with your center and your spread. All right, so if you have a skewed distribution or outliers, then you need to use median and interquartile range to describe center and spread. All right, so the heights of the students follows a right skewed distribution with a median of 65 inches, an interquartile range of 5 inches, and no outliers. All right, that is my description of the distribution. That's all you really have to do. You identify the shape, you identify the correct center and spread based on the shape of the distribution. All right, remember, if you have a symmetric distribution, you should use the mean and the standard deviation to describe it. If you have a skewed distribution, that's when you switch over to median and interquartile range. Median and interquartile range are less useful in the long run for us to use for measures of center and spread, but if they're the only ones that we can trust, then we have to use them. All right. Also, if you have outliers, then you would want to make sure that you use median and interquartile range. Identify your center and spread based on these, and also identify whether or not there were outliers. If there were outliers, state what the outliers were. State those actual points with their values. Don't just tell me there were 2 outliers. Tell me specifically what they were. So, and 2 outliers at, and then actually tell me the numbers. Don't forget your units. Notice that I included the units in my description. And I also included the context that I was talking about the heights of students. All right, this isn't just some random thing I was measuring. I asked my students for their heights. All right, so moving on from there, now we're going to take a look at whether or not the data could have been approximately normal. Now, a normal distribution is going to be a bell-shaped curve, single-peaked, perfectly symmetric, and when you look at the mean, when you go within one standard deviation, you are going to have 68% of your data. When you go within 2 standard deviations, you're going to have 95% of your data. Within 3 standard deviations, 99.7% of your data. All right, this is called the 68, 95, 99.7 rule. It's also known as the empiric rule. Why the empiric rule? I have no idea. I just know it's also called that. All right, so 68, 95, 99.7 rule, also known as the empiric rule. Now, what we're gonna do is we're gonna create a dot plot. I'm still gonna go through the process of actually doing the calculations to see if it could be approximately normal. However, remember what I said towards the beginning. This is not single-peaked bell-shaped. It's right skewed. It's very much not symmetric. So right there, you already know that it can't possibly be a normal distribution. But we're going to go through the motions just to kind of check it out and to make sure that you understand how to do that if there's a chance that it could be normal. So check number 1, is it symmetric? If not, we could actually write right now that because the data is skewed to the right, the distribution is not normal. And actually, I'm going to go ahead and write that. Since the distribution is right skewed, or skewed to the right, you can say it either way. I tend to switch back and forth. So since the distribution is right skewed, it is not approximately normal. And remember, I am capitalizing the word normal because it's a proper name. This is a very specific type of curve used in statistical calculations. Therefore, it has a capital letter because it is a proper name. All right, now let's go ahead and create the dot plot and just kind of look at how to work through this if it had been symmetric. So I'm again going to draw a number line. 61, 2, 3. So 2, 3, 4, 5. Got ahead of myself. There we go. 66, 67, 68, 69, 70. I'm trying to keep these fairly even. If they get a little bit off, it's not the end of the world. Just try not to let them get too horribly off. And since I know that's probably going to bother anyone who needs things to be nice and even, I'm going to go ahead and start at 60 instead of 61. All right, so 60, 61, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. There we go, just for the heck of it. And again, these are people's heights in inches. All right, now I want to kind of go through and make sure that each of these data points is actually entered in here. So I'm just going to kind of hold this down here so that I can read off of it and you can kind of see the numbers as I'm going through. All right, let me see. There we go. I think that's actually in frame. All right, so 66, I'm going to put that point right here. I'm going to kind of go in between for one and on the line for the second point. You want to keep the points pretty evenly spaced. All right, so 66, 64, 61. Notice I'm trying to keep these at the same level. 66 again. 67. 66. 62. 73. 64. 63. 72. 61. 62. And 70. All right, so you can kind of see how all the points are sort of grouped up over here, but then you have a few points kind of drifting off to the side. All right, now the traditional way that we would actually check to see if data is approximately normal is that we would use the mean, in this case 65.5. All right, so that would be like right in here. I'm a little bit off, but assume it's centered. Just pretend it's centered. And our standard deviation of 3.898. All right, and what we want to check for is our mean plus minus 1 standard deviation. All right, we're going to get our lower bound with the subtraction here, our upper bound with the addition here, and then we want to figure out the percent of the data that actually falls in that range. And this should be close to 68% if we're on the right track. So my mean is 65.5. All right, so 65.5 minus 3.898 gives me 61.602. All right, so right around in here for minus 1 standard deviation. And 65.5 plus 3.898. Me 69.398, which would be about in here. All right. Within these lines, I want to know how many data points are inside of there, and I need to divide by the total number I have. Now, I had 14 data points, so I should have 14 points within here. And between 1 standard deviation below and above my mean is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of the 14 points. So 9 divided by 14, not bad. Gives me about 0.6428, so I'm going to round to a 3. So 64.3% approximately. That's decently close to the 68% part of the rule. But now when we get to mean plus minus 2 standard deviations, and I want to go through and subtract another standard deviation from this and add a standard deviation onto this one. So I'm going to take this 61.602 and I'm going to subtract 3.898 from that again. 57.704, so definitely like way down here. And then take the 69.398 plus 3.898. And I have 73.296. And when I look at that percent, that would put me outside of my highest value. So now I actually have 14 out of 14, which is 1, which is 100%. Now this should only be about 95%. All right, this shouldn't be close to 100% yet. If I go 3 standard deviations out, I'm still at 100%. This is just way too, this got to 100 way too quickly. All right, so this is not approximately normal. It doesn't fit this rule. It doesn't fit the shape, and the shape is important to look at before you even start doing this. So if your shape is skewed, either left or right, and it's not a single peaked distribution, then it's not really even worth testing this part of it. You'd still need to make the dot plot in order to meet the directions, but you wouldn't necessarily have to do these calculations if you can already tell from the shape that it's not even going to have a prayer. All right. I hope that you found this interesting, and let me know if you have any questions remaining on this material. All right. I'll see you in class.